In this video, what I'm going to do is solve a practice problem, an example problem, where we're going to look at the difference between constant heat capacities and temperature-dependent heat capacities. We'll look at kind of the practical difference. We're not going to do it a lot. You'll have this problem, and you'll use this in a single homework problem, and then we'll kind of forget about it. But I think it's useful to at least see how this works, how we get more correct answers, even if we're not going to do it that often. So the problem, the scenario goes like this. We have steam, which is, I'll circle this, it's reversibly compressed / cooled. So it's going to a smaller volume. That's what we mean by compressed. And it's cooled from 500 C to 300 C at, and I'll circle this, constant pressure. And we're asked two parts. First, to determine the work of this compression, and second, to determine the heat transfer required, using both constant heat capacity and a temperature-dependent heat capacity. Okay, so to determine the work, I have kind of the setup that we're looking at here. We're looking at our initial temperature being 500 C, our final temperature of 300 C. We know this is reversible and constant pressure. And we're told that, P1 is equal to 300 kilopascals, as is P2. To calculate the work for this reversible process, we're going to be using our equation for calculating work for reversible processes. That's the integral from state 1 to state 2 of P d specific volume. Because pressure is constant, we can pop it out of the integral, and we get that the work is equal to pressure times the change in specific volume. We can flip this around because for an ideal gas, right, V equals RT over P. Specific volume is RT over pressure, so we can calculate the work as the pressure as pressure multiplied by RT2 over P minus RT1 over P. The P's cancel out, and this is just RT2 minus T1. I didn't leave us too much space, but we can finish calculating the work. That would be R, which I have written down from our tables up here, so we could look that up. 0.4615 times the change in our temperature, 300 degrees. We would get a work of 93.4 kilojoules per kilogram. Sorry, the change in temperature is 200 degrees. So 200 times 0.4615, 93.4 kilojoules per kilogram. So there's the answer to the first part, finding the work. Right. The key part to remember is this is really the equation here that we're using, and when we go through some of this stuff, we're simplifying that equation, but that's really the equation that we're depending on. That's the equation that's calculating work. Everything else is just us kind of simplifying it and massaging it to the form that we want. Now to calculate heat and internal energy, right, heat is going to be path dependent. Internal energy will not. So we're going to find U first, delta U first. For a constant, this is going to be a delta U problem. So that's going to be a constant volume heat capacity, right? Delta U equals, right, the volume is changing, but we use Cv for finding U. So that equals, if we're using constant Cv, that's 1.410. Again, I looked these up before. We're going to be using Cv for this first problem. 1.410 kilojoules per kilogram Kelvin times delta T times 300 minus 500. Guess that would be degrees C, but because it's a delta, that's also Kelvin. So delta U equals negative 282 kilojoules per kilogram. And we could find that, we could find Q then from that. Just of note, from our steam tables, delta U, if we looked up the numbers, would be 2806.7 kilojoules per kilogram minus 3130 kilojoules per kilogram. So delta U would have been equal to negative 323 kilojoules per kilogram. So we're not super close. If we use a constant volume heat capacity, that's what we get, or a constant heat capacity, temperature independent, just a constant value heat capacity. That's what we get. The correct answer is this. So this is Cv is a constant. This is the correct answer from our steam tables. We're at least in the ballpark, the right idea, but certainly not the right answer. 282 versus 323. A better way is to recognize that really the heat capacity is something that changes with temperature. As we showed in the graph in class, these are heat capacity values. The ones that we see in our table that look like a constant, that's really just a constant. It's just kind of a value that's chosen. And really these are values that are going to change with temperature. The value that we get when we look at the temperature dependent heat capacity value, we get this bottom line here. And really it's a CP value. We'll deal with that in a second. It's a polynomial equation. It's just this big ugly equation to fit the temperature dependent heat capacity. And we choose these kind of polynomials because then we can fit a lot of different behavior. It's just an equation to fit data, right? You get a big enough polynomial, you can fit anything. That's all that this is doing. And we have four different coefficients on our polynomial. We have these values theta, where theta equals the temp over 1000. So we'll have to deal with that. We'll have to deal with that as well. Okay, so how would we do this? Well, we would find the exact same equation. Delta U equals the integral from T1 to T2 of Cv dt. But now Cv we have to replace with the temperature dependent function. So it's not a single value, it's now a function. For an ideal gas, remember, we can relate Cv and Cp with R, with the gas constant. So Cv equals Cp minus R. So we have a table with a bunch of Cp values. We can very easily get the Cv values by just subtracting R. Okay, so let's do the integral. It would be delta U, the integral from T1 to T2 of C0 plus C1 theta plus C2 theta squared plus C3 theta to the third minus R d temperature. So that whole thing in brackets is Cv. We have a little bit of a problem because theta is not temperature. Right? T equals 1000 theta. So we can get from temperature to theta, from theta to temperature by a factor of 1000. So we'll do that. And what this would functionally change is that delta U would now be equal to 1000 times the integral from theta 1 to theta 2, right? We can take our dt and change it to a d theta, change the integral bounds to theta. Then this would be, if we plug in our coefficient values, 1.79 plus 0.107 theta plus 0.586 theta squared minus 0.20 theta to the third minus R, which was 4615. All of that d theta. Okay, so if we go through and do the integral, then delta U equals 1000. That's out in front. And then our integral is now combining this constant and this constant. We'll combine those into our first term. 1.329 theta plus 0.107 over 2 theta squared plus 0.586 over 3 theta to the third minus 0.20 over 4 theta to the fourth. This would all be evaluated from theta 1 to theta 2. Theta 1, right, this equals T1 divided by 1000. Theta 2 equals T2 divided by 1000. So we would be evaluating our integral from a value of theta 1, 0.773. And theta 2 is 0.573. Okay, so to actually evaluate that, we would first plug in 0.573 in place of theta. Then we would subtract the same function with now 0.773 in place of theta. I'm not going to do that, but you're welcome to. The answer that we would get would be delta U equals negative 321 kilojoules per kilogram Kelvin. Sorry, kilojoules per kilogram. So if we look back at what our previous results were, right, we could find work. We could use this equation here to find the change in internal energy, or we could use the steam tables, right? Here we used the steam tables. The steam tables gave us the correct answer, negative 323. When we used a constant heat capacity, we got negative 282, so in the right ballpark, but certainly not the right answer. When we were able to actually go through the details, use a temperature-dependent heat capacity, then we got to a value of negative 321 kilojoules per kilogram, much closer to the actual true value for this problem. So we can see there's not a whole lot of real understanding gained, other than the fact that we should really remember that these heat capacity values, they're not constant values, they're really temperature-dependent functions. We can deal with them if we want to go through a little bit of extra math. But most of the time, for the sake of this course, we'll just assume that they're constants and just kind of play along, pretend that they really are constant values, even though we know in the back of our head that they really are these more complicated functions if we want to get the real results. But certainly the constant values, they're good enough for us to really get a good conceptual understanding of what's going on and how things are behaving.